All right, this video is going to talk about compound events, or basically what I like to call the multiplication rule. What happens when we're trying to do two different events at the same time, right? One event and another event. So note that keyword and. How do we find the probability that, again, they can occur together, right? The probability that you're doing one thing and another one, right? It comes down to sort of two scenarios. You can either be two independent events, independent meaning that one event doesn't affect the next one, or dependent events, where again, the probability of the first one is going to affect the probability of the second one. A good example is down here at the bottom. Let's say we're going to take a deck of cards, regular deck of 52 cards, and we're going to draw both a heart and a spade, right? But now there's a major difference between these two questions. In the first example, well, let's probably that we draw a heart, then a spade, after replacing the heart, after making that deck full again, right? The first card's going to go back in. Well, the probability of a heart, right? There's 13 hearts out of that 52 card deck. There's also 13 spades. And because we're going to put that heart back, it will still be, again, a 52 card deck. So the probability of a heart and a spade, we're just going to multiply those. Essentially 1/4 times 1/4 is 1/16, or basically 0.0625. Right? Again, we can represent that either as fraction or decimal. Now, that means those two events were independent. When we put that heart back after drawing it, now it's a full deck again, and the fact that we drew a heart in no way affects whether or not the next card we draw is going to be a heart or a spade. Right? But now down at the bottom, what about the probability of a heart then drawing a spade? Well, if the first card is going to be a heart, the probability of a heart is still 13 out of 52. But the probability of drawing a spade, given that there's a heart missing, means there's 13 spades to choose from. But now there's only 51 cards in the deck. So that's going to change our probability, right? It's not going to be the same as it would have been previously there. Right? And if we multiply those two fractions together, you'll notice we get 0.637, or a slightly greater, 0.0637, I should say, slightly greater probability, which makes sense. Excuse me. It makes sense because, right, again, there's another card missing. There's more of a chance of drawing a spade given that there's not another heart getting in the way, right? We've already removed one of those hearts. So it makes sense this probability came up just a little bit. Just a little bit. Again, we call that a dependent event. The probability of that event happening, the spade being drawn, given that the heart is missing, changes that probability, right? The probability of a spade and the probability of a spade given we already removed a heart, those are two different things. Those two things aren't going to be equal to each other, right? That given idea is what we call a conditional. A conditional probability is one where, again, the probability of B, given that A already happened. One way to represent that is sort of that up and down bar here. Probability of B given A, if you ever see that symbol, right? Again, both of these fall into the multiplication rule. Both of them are and, right? We're doing two things. Draw one card and another one. Both of them are sort of the intersection of those two events, right? We want the probability of A, probably the first thing happens, multiplied by the probability of B. The only question is, do we want the probability of B as though A never happened, or the probability of B given that A already happened, given that A affects B, given that it was conditional upon B? Let's look at those conditionals sort of in a slightly different way. So again, a woman has two children, one of which is a girl. Find the probability that the other child is also a girl. Well, again, given that we know one of them is a girl, that's going to change this scenario, right? And you might be thinking, by the way, on this one, this is a little bit tricky. A lot of folks look at this and say, oh, well, if one of them's a girl, the other one's either a boy or a girl, it's 50-50 chance. Well, that's not quite the case. Let's use a Punnett square to help ourselves out here. If one of the children could be either a boy or a girl, the other child could be either a boy or a girl, here are the four scenarios that could happen. Either they're both boys, one of them's a boy then a girl, or else it could have been a girl then a boy. And then the last one, again, they could both be girls. Again, that conditional idea is saying, well, given that one of them is a girl, I can actually rule out, right, in that black square there, that they're both boys. I'm going to rule that out because, again, we already know one's a girl. That's not even a possibility. The other three squares, though, all have at least one girl. Only one of them has a girl and the other is also a girl. So again, 1 out of the 3 scenarios, that's the probability, again, that we're going to have 2 girls given, right, that one of them is definitely a girl. Given that one of them is definitely a girl. So again, we could have rewritten that notation. Probability of 2 girls, right, given, right, 1 girl. Given we're definitely 1 girl or more, right, or more. Let's try the one down at the bottom here. 3 cards are in a mixed bag. Again, there's 1 card that has 2 red sides, 1 has 2 white sides, and 1 has a red and a white side. 1 card is pulled from the bag out of the set on the table. It shows red. What's the probability the other side's also red? Given that we're seeing a red card, there's that conditional idea. Given that one of them is red, what's the probability that, again, the other side is also red? Well, let's think about this scenario. We've got 3 cards. There's a red, red, white, white, and red, white. I'm going to name the sides. I'm going to say there's a red, we'll call that A. There's a red called B. Those 2 are kind of in 1 card. There's the card with the white, white. We'll call them C and D. And then the red and white, that's E and F. If the side showing were A or B, right, then we know the other side is red. So there's 2 scenarios, right, that we know of where we've got red and red. If the side showing were E, because we know we're guaranteed it's red, right, we're E, then the other side would be white. I'm not worried at all about, again, either side being white, being that white card, because we're guaranteed that's not the card, right? So now we have to say, okay, well, that means there's 3 scenarios. 2 of those scenarios have the red card showing. So again, 2 out of 3 things. We want one of the 2 reds that has the other red on the other side. We don't want the one, right? There's third scenario where it's red and white. What do we want versus what could happen? I hope that helps you think about those conditionals. Let's go back to a couple more examples real quick. Dependent events, again, are events where the first event affects the second one. It changes the second one. So again, the probability of B is different than the probability of B given A, right? A affected the outcome. So if drawing 2 marbles from a bag containing 3 red, 3 blue, 2 yellow marbles without replacing, again, that's the key, without replacing the first marble, that immediately tells us we're going to have that change. What's the probability of being both red marbles? Well, the probability of the first red marble, right? Let me get a slightly different color here for you. Probability of the first red marble would just be 3 out of the 8 marbles. And the probability of a second red marble given that we had a first red marble. Well, in that case, there's a red marble missing, so there's only 2 red marbles left out of the 7 marbles left, or essentially 6 out of 56, or 3, if we reduce it, out of 28, right? Possibilities. Let's look at this second one. A quality control procedure for testing disposable cameras consists in drawing 2 cameras out of a lot of 100, right? We got 100 random cameras. We're just going to pick 2 of them. Only if both cameras are defective do we throw out the whole lot, right? Otherwise, we just assume, well, there must not be so many defective cameras to worry about. Find the probability that a lot is accepted if it contains 10 defective cameras. Well, we're sort of checking our procedure here. One scenario, or one way to think of it is, out of the 100 cameras, we could draw one of the 10 defective ones, right? Or, and at the same time, then, in the second camera, well, if there's a defective camera missing, now there's only 9 defectives out of the 99 possible. Another way to think of that, out of the 90 good cameras, we're not going to pick any of them. What's probably out of the 10 defective ones, both of the cameras we picked came from the 10 defectives. Divided by, here's all the different things that could happen, right? 10C2, picking 2 cameras out of the 100 cameras. Either way you think about it, both of those things are going to come out to 0.0091. There's only a 0.0091 chance, right, even with 10 defective cameras in there, that we pick 2 defective cameras, that we reject the whole lot. Well, probability it's accepted then, right, probability of accepting the lot is really 1 minus the probability of rejecting it. So we're going to say 1 minus 0.0091. There's still, even with 10 defective possible, there's still a 0.9908, right, or 0.9%. A little over a 99% chance that we go ahead and sell these cameras anyways. You can decide if that's a good idea or not with 10 possible that just don't work. Independent events, on the other hand, again, let's think about that. An independent event is where if the probability of B, right, is the same whether or not A happens, probability of B given A, it's not going to change, right? What happened first doesn't change what happens second. So rolling 2 dice, what's the probability of rolling a pair of 5s? Well, the probability of rolling a 5 the first time is 1/6. The probability of rolling a 5 the second time, given we rolled it the first time. Well, the first dice doesn't in any way affect the second one. So again, there are still a 1/6 chance on that second dice of rolling a 5. Doesn't matter what the other one did, right? That given 5 really doesn't matter. So again, it's going to be a 1/36th chance of that happening. Another way to think of it, again, in softball, if you're up to bat, your first at bat, your second at bat really shouldn't affect each other, right? If you're a good at bat or a good player doesn't think about their last at bat. So a softball player has a 0.7 on base percentage. They get on base about 0.7 or 70% of the time. What's the probability of in 3 at bats they get on base all 3 times? Well, it's going to be 0.7 for the first at bat, and should be again 0.7, right, in the second at bat, 0.7 in the third. If those at bats don't affect one another, there's 70% chance each time, and basically 0.7 to the third power, or 0.343, right, would be our probability of success, right? Or probability of 3 on base times. Now, this is a pretty good batter. There's 70% chance of getting on, more than half the chance. But again, getting on 3 times in a row still is not a monster chance, right? So 0.343. Not bad. A little over a third, but still not great. All right, hopefully that helps you again with dependent and independent events. If you need to know more about and, you can always talk to your teacher. There is another video. Feel free to watch that as well. Again, it's going to talk a little bit more about what if we say or. What if we're doing one event, but again, 2 different things could happen within that event. Have a great day.